Lila, here's a hot dog. If I asked you to cook it, what are the various ways you could cook it?
Well, you can boil it, you can fry it, you can barbecue it on a stick.
You can put it in the oven and roast it, I assume, too.
Yeah.
Have you ever electrocuted it?
No.
Well, that's what we're going to do today. But it's a very dangerous experiment. So I don't want you to repeat it at home because we're going to put electricity right through the hot dog.
Right through it?
Right. First of all, here's the hot dog. I will put a fork in one side like this and another fork in the other side like that. Now I'll connect up electricity. This is why I say it's dangerous, because you don't want to fool around with electricity like this at home.
Yeah, you could get electrocuted.
Yes, you could get electrocuted, like we're going to do to the hot dog. Now, I have an extension cord that I can plug in, and we'll turn it on, and then I want you to think about what's actually happening.
Okay.
Okay, there it's on. Now current is going through the hot dog. How come current's going through it in the first place?
Because the...
Don't touch anything.
I'm not going to.
Okay.
The little things are connected to the forks, which are metal.
Right.
And they're conductors.
Okay, they're conductors. But what happens when the electricity gets to the hot dog?
It goes through it.
It goes through it because there's salt in the hot dog.
Salt?
Salt, yes. And that makes the liquids inside the hot dog a sort of semiconductor. At the same time, as the electricity is going through there, it's meeting resistance. There's a whole series of electrical components called resistors that hold back the current. And whenever you hold back the current, you'll give off heat. So that's what's happening to the hot dog. See, it's beginning to bubble right there by the fork?
Yeah.
Okay, now, as the current's going through there, that resistance inside the hot dog generates heat. Look, it's smoking. Hear it?
Yeah.
There, we're cooking.
Now it's starting to swell.
There.
Oh, it's getting bigger.
Yes, now it's really cooking. Okay, let's turn it over once and see how we're doing. One more little shot. Ooh, it's hot.
It's split open.
Yes. Okay, I'll turn out the current, take out the plug so we're sure that it's off. Now, the nice thing about using forks to cook a hot dog, you can use the forks to eat it. Look at that. It's a little hot yet. One for you and one for me. Blow on it and cool it off and try an electrocuted hot dog.
Those are excellent.
Thank you. Stacy, you know what a lever is, don't you?
Yes, like a seesaw.
Well, that's one kind of lever, and here's the sort of seesaw right here. Well, there are actually 3 different kinds of simple levers, and I've collected some common tools from around the house to illustrate the 3 different kinds. Let's start with this kind.
Okay.
The fulcrum, or the pivot point, is in the center, in the center section anyway. Then you want to accomplish some work, so I'll put this book as a weight over here. Okay. And then you have to apply effort over here.
To lift the book up.
Right, to tilt the book up. So those are the 3 important parts of a lever. The fulcrum, the work, and the effort, okay? What would happen, by the way, if I move the fulcrum closer to the work?
Well, I'd have to do a lot more distance to get the same amount of work done.
Yeah.
Then in the middle, it was an equal distance.
But you didn't have to exert as much effort over there.
Right, it was
But
really
you
light.
moved through a greater distance. What if I put it up here?
It's heavier, but I don't have to move as
Same
much.
weight.
Well, it feels heavier.
Feels heavier because you're not being able to exert as much force because of this short distance and that long distance. Okay, so when engineers design tools based on the lever principle, they use those principles, keep those principles in mind. For example,
The scissors.
the scissors. Okay, where's the fulcrum, the pivot?
Right here in the middle.
Where are you going to the effort?
Right here,
Yeah.
the
And
handles.
where do you accomplish the work?
Here at the sharp
Yeah.
point.
And why is the pivot point so close to your fingers?
Well, so I just have to exert a little bit, and I get a lot out here.
Right.
If you put it closer, then you can just do a little bit.
Right.
A lot more.
In other words, you want to get greater distance. You want to move through a greater distance when
Right.
you cut. Compare that to this lever, which is based on the same principle.
I mean, you have to do a lot to make this, to do a little up
Yes,
there.
but you can pinch with greater force.
Right.
Right. Which is why they design a pair of pliers using that principle. Now let's go to the next one.
Okay.
I'll put the fulcrum at the end, like that. I'll put the book here. That's the work. And you apply the effort there.
Well, I move a little bit, and that moves a lot, and it's
Wait a minute,
heavier.
wait a minute. You move what? You move
Oh,
a
a
lot.
lot, and this moves
And
a
it
little
moves
bit.
a little. But you
But
could
it's heavier.
Yes, but you could exert now. The closer I move it to the fulcrum,
Right.
the easier it is for you to do it because of the leverage.
A nutcracker?
Isn't that the fulcrum is up here, right?
Oh, I see. And you put the force down here,
Yes.
and you can apply more pressure.
Yes.
Right there.
And if I put my little finger right there, you
I
could
could pinch
crunch
it.
it. Right. How about this one? Same idea?
Well, yeah, a garlic press, because I need to move a lot to get a little up here,
Right.
but there's greater force.
Right, because you want to squeeze out the juice from the
Right.
garlic. Okay, there's one more left. This time, I'll put the fulcrum at that end where you are,
Okay.
and I'll put the work way out here, and you have to exert the pressure by pulling up over here.
Okay.
I'll hold it so it doesn't move. Now,
Well, I
watch.
move a little bit, and that moves a lot, but it's heavy.
Yeah, it seems heavy. You have to exert a lot of force. Why would you want to do that? Notice the speed or the distance through which it goes. You move that through a little distance, watch what happens to the book.
It moves
Through
quite a
lot.
bit.
Yes.
Sugar tongs? Oh, I see. Here is the pivot point,
Yeah.
where you apply the pressure
Yes.
or the work, and here's where the thing is going to be done.
Yeah. Now, can't you think of another example that's a little more common, in which there's a pivot point at the end, the fulcrum. You exert a little force here through a small distance in order to make that go much faster up here, which is what happens, right?
Right? Baseball bat?
Yeah, take a look at a baseball bat as a simple lever. Where does it pivot?
Right here
Yeah.
at the end.
Where do you apply the force, the effort?
Right here.
There. And where you're trying to make that go?
Fast.
Fast. So whenever you use a baseball bat, you're using that simple lever. And other levers, athletic equipment works on the same idea. Tennis racket, hockey stick,
Oh, I
golf
see.
club, all based on a simple lever. How come a fly can walk on a wall without falling off? Well, take a close look at a fly's foot. The two claws are used to grip a rough surface. Between the claws is a sticky pad. From underneath the pad is the light-colored spot. The sticky pad holds the fly to a smooth surface. The claws and the sticky pads on the fly's feet means it can walk just about anywhere, even upside down on the ceiling. Billy, here's a book that has thousands of names in it. You know, when fathers and mothers are going to have a baby and they don't want name to choose, they can get a book like this and look up all their suggestions. In spite of the fact that there are thousands of names in here, I am going to write down a name.
E F R E M
Ephraim. Okay? Now, you choose a number from 1 to 10 and put it down here, and then another number from 1 to 10. In other words, 3 different numbers. Write it down up there in the top, right over here. Now, I have no idea what number you're going to choose.
6 45
Okay? Now I want you to reverse those.
5, 46.
Now subtract one from the other.
Okay, you can't take 5 from 6, so you have to carry.
Mm-hmm.
So 3, carry the 1, that's 15. And that equals 9. No?
6 from 15, right, 9.
9. Those are
Okay?
Okay. Can't take 3 from 4, so you cross up with a 6 and put a 5.
Okay. 4 from 13.
And then, let's see, that's 9.
Mm-hmm. Now what are you going to get here?
0.
Okay, put a 0 down there.
0.
Now reverse that again. 9,
9.
9, 0.
0.
Okay, add those up.
Add them? Okay. 9 plus 0 is 9.
Mm-hmm.
And that's 18. 9 plus 9.
Mm-hmm.
And
18.
8,
One
carry
to
the
carry.
1. And that's 10. So you get 1,089.
If you will look at the 10th word on page 89 of this book of thousands of names, see what you find.
Okay.
$10.89. What do you got?
Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
What's the word?
Ephraim. How'd you do that?
Well, I memorized every single word in the book.
Oh, you did not. You couldn't memorize every word in this book.
Well, this is based on the findings of mathematicians who like to play with numbers. And they found that when you do this, what looks like a very calculated and very complicated calculation, that you end up with some very interesting things. Who are you going to play this one on?
My best friend, Michael.
Okay. Now, you remember what to do? Take another number and put it over here. And you'll see what happens.
4, 2, 3.
Now, what's next?
You got to reverse them.
Okay.
3, 2, 4.
Then?
Subtract them.
Mm-hmm.
So you can't take 3 from 4, so you gotta carry again. It's 1. Equals 9.
Mm-hmm.
And then can't take 1 from 2, so you gotta settle. Put a 3. That's 11. Take away 2 is 9. 3, take away 3 is 0.
Okay. Now, what did you do next?
I turned them around.
Turn them around.
9, 9, 0.
Then what?
I add them.
Mm-hmm.
That's 9. That's to be 18. Carry the 1. And that's 10. And it equals the same.
Right. So regardless of what 3 numbers you choose up here, if you do these calculations like this, you always end up with 1089. So you look up in a book, like what? You don't have a book of their first names.
No.
How about
Dictionary,
dictionary would be good.
encyclopedia,
All right.
atlas,
Telephone book. Yeah, telephone book is great because you can look at the 10th name on page 89. And by the way, if you do this and you turn out here with a negative number, if this number is smaller than this one, then you have to add a negative number down here. Okay, you got it?
Yeah.
You gonna try it on Michael?
Yep.
Okay, good luck. It's based on these strange characteristics of our number system. See, I've made a little lamp out of stuff I found around the house because I have a little problem for you. Here's the situation. A storm. Electricity is out completely. No candles, no kerosene lamps, no flashlights, and it's up to you to figure out how to help your parents by making some source of light. Okay? That's your problem. How does a kerosene lamp work?
Well, there's oil at the bottom, and then there's a thread called a wick that goes right up to the top. And when you light the wick, the oil flows up the thread and keeps the flame continually burning.
Okay, so that's what we have to reproduce somehow with stuff you can find around the house. First of all, I said no kerosene, so what are you going to use in place of kerosene? Got an oil of some kind. What kind of oil have you got around the house?
Cooking oil.
Like that.
Yeah.
That's corn oil. Okay, now we have a supply of oil or for fuel. What's the next thing you need?
Wick and
Okay. You got
thread.
string?
Yes, I got lots of it.
Lots of string? Okay, well, you have to make that into a wick somehow. And here's how I made mine. See what that is?
Yeah. You put it through a bolt.
Yes. You got nuts and bolts around the house?
Yeah, I got.
Okay. So you force a bunch of them through there in order to make a little wick out of it. Then you need a container to put it in, and I use these little aluminum things. Here, you spread the bottom of the wick so it goes all over and I'll move this one out of the way. That's the idea. Okay, now. Okay, now we need a supply of oil. Simply pour a layer of oil on there. Okay, that's enough for now. Now you gotta light it. Now it doesn't light easily because it's not nearly as flammable as kerosene, so it might take a little while to get it going. Got it? Try under the edge over there. Okay, now it'll gradually get bigger and bigger and bigger. And the one I made earlier has been burning for, over an hour. And it hasn't really used up the supply of oil yet. So now how are you going to, when this emergency takes place, how are you going to help your parents? What are you going to do?
Well, I'll take a nut and some twine and stick the twine through the nut and then put it in one of these aluminum muffins and put them in there and spread them apart and then put some cooking oil and then light it.
All right, and you've got an emergency candle. Very good, Eugene. You're going to play an unusual safari guessing game, going to far-off places to gather the ingredients for a common food you've eaten many times. See how soon you can guess what that common food is. First, to the tropics. Most plants are grown for their fruits, leaves, or roots, but these are grown for their stalks. Presses squeeze out the juice, which is cooked into a thick brown liquid. More processing removes the rest of the water and impurities to produce the familiar white crystals that are the first ingredient of the mystery food, sugar. Next to farms that specialize in raising cows and, of course, milking them. Obviously, the next ingredient is milk. Finally, to Africa or Latin America, where this tree grows. On it are pods about the size of a cantaloupe. They're sliced open to remove the 30 to 40 beans inside. The beans are heaped into piles and allowed to ferment, a natural ripening process during which chemical changes create their characteristic flavor. Another 6 or 7 days of drying in the sun changes the color to dark brown. The beans are shipped to a factory where they will be combined with other ingredients to make the mystery food. Different varieties of beans are blended together and then roasted in ovens. The hard shells are removed, the inner part ground up to produce a rich, smooth liquid. The sugar and milk are added, and the mixture is ground over and over again until the particles are very fine. The warm mixture is poured into stainless steel forms. When cool, the final product is removed from the forms and sent to the automatic packaging equipment. Of course, by now you've identified the mystery food. The juice of the sugar cane, milk from cows, and the beans from the cacao tree have been combined to make milk chocolate. Balloon full of water, Stacy, and a quartz watch. They have something in common.
What?
Well, first of all, I've taken that quartz watch apart so that you can take it apart yourself and turn it over.
Okay.
But have you ever had a wind-up watch?
Yes, I have.
Okay, what makes it keep time?
Well, there's a little spring inside of it.
Mm-hmm. And there's a balance wheel that went back and forth and back and forth and back and
Yes.
forth. There's nothing like that on a quartz watch, is there?
No, there isn't.
Take the top and flip it over.
Okay.
Okay. Now, there's the little battery.
Yeah.
Okay. Now, what is it that makes the quartz watch work?
Piece of quartz.
The quartz, right. And there it is right there. See that little canister-like looking thing?
Yes.
Inside there is a tiny piece of quartz.
It's pretty small.
Yeah, pretty small. And the battery, which ordinarily goes here, supplies current over to this little piece of quartz. And that's how the quartz and the balloon are alike. Here, tap the balloon on the top. Tap it a little harder. Now tap it softer. See, regardless how hard you tap it, it always vibrates at the same frequency.
Yes.
That's its natural vibrating frequency. Well, the little piece of quartz inside there has a natural vibrating frequency also when you put an electric current on it, except it's thousands of times per second.
Oh.
And that's the place of the balance wheel. Here's a puzzle for you, Michael. See, I have this brick hanging here
Yeah.
by a stout cord from the swing. But part way up, here's a nice thin string.
Oh, just like this one.
Yes, and down at the bottom, there's another little thin string. What I want you to do is to be able to break the bottom string without breaking the top one.
Well, I don't know how.
Well, it has to do with mass and weight. First of all, what's weight?
Well, weight is when gravity pulls it down. Something
And
down.
you put a scale in the air and
Yeah.
and you measure how much the force of gravity is pulling. But you could take this brick up into outer space, no gravity.
Oh, so you mean like there's still mass in outer space, but there's no weight.
Right. Okay, so this brick at the present time has both mass and weight. Gravity's pulling down on it, right? But the inertia really, scientifically, the mass is determined by its inertia. Now let's see if I can explain. Have you ever heard of
what's
that?
inertia?
Well, let's see. If this were in outer space,
Yeah.
the mass of the object would be determined by how much force it takes to get it to move.
So that's what inertia is?
And that's the inertia. The
Oh, I
inertia
see.
is the tendency of an object to stay at still if it's still until a force of some kind moves it. So as
see.
this brick is sitting here, it has both mass and weight. If you jerk quickly at the bottom string, the inertia of the brick is still going to be there, right? And you're pulling against the inertia of the brick,
So the string will break.
this string would break, right?
Yeah.
Now what if you pull slowly?
Well, then,
You'll overcome this inertia. Then gravity and inertia together.
oh, I'll break this string.
You sure you got it now?
Yeah.
First you're going to break the bottom one by doing what?
Pulling it quickly.
To use the mass of the brick. Now then when you pull slowly, what'll happen?
This one will break.
Okay, are you ready?
Yep.
Let's test the theory. You're going to do it real quick.
Okay.
Okay.
Broke.
Just like that. Okay, now you're going to break the top one, hopefully, by pulling it slowly. There you go. Here, I'll take the string.
Okay. Slowly.
Slowly. There. So now you know the difference between mass and weight.